welcome again to the second day. So, well, in fact, it should be the third, but we know there was no first. So the agenda of today is very easy. So first, Andres will finish with some practice of what we did yesterday. It's a practice, right? Yeah. And then by 9:30, so Javier will take over the mic and do some description of network models that we have. And finally, by 11:30, so we will have a break in the middle, and then by 11:30, one of our colleagues at the MIT Institute, he will come to explain our own expansion model that is called macro, that it interfaces with several energy vectors, electricity, hydrogen, and also it considers like the CO2 system. Okay, so this is it of my side. Andres. Okay.
Okay, let's summarize what we saw yesterday. First, we were interested in the medium term. The medium term means a year or something around a year. Can be months or can be up to 2 years, okay? So we are interested in analyzing how to organize, how to optimize the hydro inflows we are receiving in our reservoirs. And therefore, we can save the water for future, or we can use that water now in order to optimize the hydro scheduling, okay? So this is the main idea of this hydrothermal coordination model. And we emphasize the model in two things. One is the topological relations. So we have basins and we have cascaded reservoirs connecting them, okay? So, and we saw some of the possibilities, for example, this one. So we have many reservoirs, we have power plants at the bottom of each reservoir, we have the pumping possibility, either moving downstream the water or upstream, and we also have, let's say, that they are connected by the rivers. So the water that is turbined in one power plant goes to the following one, and so on, and we must take that into consideration. So this is the first thing we emphasize in this problem, and the second thing was the stochasticity. So there is a huge uncertainty regarding how many hydro inflows, how much hydro inflows we will receive in the next months, in the following months. And therefore, we need to take that uncertainty into account. How we do that? We create a scenario tree. We generate that scenario tree replicating the statistical properties of this uncertainty. Okay, that is the way we introduce the data. First, we discretize the historical data in a small number of branches, and then by means of this scenario tree, we consider the spatial and temporal correlation of the hydro inflows. So we consider that, for example, if the water is coming from the Atlantic Sea to the shore, to the New England, then there will be correlation among these different hydro reservoirs located in that area. And also, if this week is raining, next week has a higher probability of being also a rainy week. Okay, so by showing this profile, we were able to plot the uncertainty. Taking both things into consideration, then we are able to create the scenario tree, and this scenario tree was represented as a clustering procedure, and this is just how we think or how we fit the scenario tree in the historical data. That corresponds to historical data for 52 weeks corresponding to a single reservoir, and this is the scenario tree we have created. You can see that we are able to reproduce the peaks, the hydro inflow peaks, and this is the structure of the scenario tree. So we are having no openings, no branches in the first 4 weeks, then we open 2 branches, then 4 branches, and then 8 branches. So this scenario tree matches the properties, the statistical properties of the previous historical data. And then we develop a model, a prototype. I just want to emphasize this equation in order to see how both things that I have mentioned are affecting the equation. This is the inventory balance, the water inventory balance for every reservoir, okay? Basically, we say the water we have starting this week plus the water we receive minus the water we use for producing electricity will be the water at the end of the week, okay? This is the water inventory constraint, and here we are considering several things. So first, R corresponds to the reservoir volume. P minus 1 is the end of the previous period, so the end of the previous week. R is the reservoir, and omega prime corresponds to the ancestor in the scenario tree. So the scenario that is the ancestor, the father of the current scenario, okay? So we are in a structure, in a tree structure, and the ancestor from the previous period is represented by this omega prime, okay? So this is the volume at the end of the previous week minus the volume at the end of this week plus hydro inflows minus spillage plus the spillage coming from the upstream reservoirs. So all the water that is being spilled in upstream reservoirs comes to our reservoir, okay? Plus the water we have pumped using a pumped hydropower plant from another reservoir, minus the water, this is the water we are turbining from upstream hydro reservoir, the water we are extracting from this reservoir, plus the water we are pumping to this reservoir from another pumped hydro storage plant, minus the water we are extracting with the current hydropower plant, pumped storage hydropower plant, okay? So here, by means of these terms, by means of these relations, we are considering all the possibilities of water coming to a certain reservoir, taking into account the topological constraints or the topological relationships where the power plants are located, how much water I'm pumping or I'm turbining from the reservoir, and the relation, the scenario tree dependencies is by the consistency between omega and omega prime. Omega will be the current scenario, and omega prime will be the scenario from the previous time period. Okay, let's go down to the prototype. First, you must install GAMS. Have you been able to try GAMS? Just go to this web page, GAMS download. So, gams.com download. Then you will have different versions, either for Mac OS or for Windows.
GAMS is a very well-established software used for optimization models. It's used a lot in the power industry,
So
also in other sectors.
Yeah, is the leader in algebraic modeling models, and was invented by Alex Mearos, and was developed, that at that time was the World Bank.
And at the IAT, we have developed many models for the industry written in GAMS. It's true that since, I don't know, 10 years ago more or less, we started developing open source models, especially with Python PyMO, like the models shown yesterday. But GAMS is still it's a very robust and
So,
well.
Once you have installed the GAMS, you double-click, at least in Windows, will be something like that, double-click that application. In Mac will be located somewhere. Again, install the application. Then you must go to Canvas and open the GAMS license that is located in Canvas.
Yes, because the GAMS, when you install it, you have a student license. But for running these models, that's not enough. So GAMS
Provide us
for this course a temporary license for, I think, for 3 months, something like that, that can be used for didactical purposes.
So once you have, let's say, opened the GAMS license, you will see access code. Once the installation is close to the end, it will ask you for the GAMS license. And in the GAMS license window, you will have the possibility of selecting the latest one that will says introduce from access code and copy and paste the access code in this field. So in the installation process, at the very end, you will be asked for a license. In the license, you have the possibility of introducing the access code.
Yeah, it's hard.
So it's huge file, it takes some time to download and to install.
No, it's just, I got the email, it's just still installing.
And it's installing. Okay. It can be installed in both Mac or Windows or Linux. Anybody has ended with the process?
The license has not been accepted, but it's open.
Why you have not go to?
I put the access code and then that message appear, but I close it and then it opened.
And the problem is that you are not going to be able to run that size. This is the installation. You have done the installation now. Here,
Yeah.
have you copied the full code from the GAMS license?
No, hold it is.
The GAMS license is in Canvas.
No, but yeah, or is it like this?
It's like a collab. Linux, Google Colab is Linux. So what did you want?
Our GAMS installed in a Linux computer because she downloaded an exe file.
It's okay.
No, I don't know how to install. What is the GAMS license? This is
Here, the access code.
without the
Yeah.
At least this is the same that I have used. So the access code can be seen here. Ends in 389. The access code we have provided.
Ends in 389.
Yes.
Mine ends in 385.
385, yes. Sorry, 385, yes. And select this code and plug or put in.
No, I got a pop-up that said could not write license to file.
Yeah.
What?
I got this pop-up when I tried to find it. On the last screen, sorry, the touchpad, you're gonna use the little.
No sé por qué no está.
Yeah, it came up when I went to, it's like, it's like, and I had a license
you selected the latest
Yeah.
option.
There's just a little checkbox on this. Yeah. Looks like it's right. Well, it's okay.
What is the problem?
There's a checkbox at
The
the bottom.
checkbox at the
Ah,
bottom.
okay.
There's like
You got it? Great.
view,
Yeah.
License. Okay, so we have been able to install the GAMS. We can proceed and download from this web page. You can download the hydrothermal coordination model. So go to this link and then download the. It will consist of an Excel file, the GAMS source code, and some text files corresponding to the case study. So you see in the slide 123. Will be a zip file. You need to uncompress the zip file. And then have you been able to download the zip file and to uncompress it? Okay. Then you can open this file, the GAMS file, start gen light SHTCM GMS. Okay. So let's go there, and we will open. So if you open the GAMS file, you will get, it will use the GAMS Studio, okay, that is the environment for developing and running GAMS files. Something like this, okay? So this is the GAMS Studio environment where you are opening the GAMS file, call start gen light and stochastic hydrothermal coordination model, okay? And then in order to run, you must copy these 3 parameters in this window. Copy the 3 parameters in this small window, and then click in the green arrow. Anybody else? Anybody has been able to succeed running the model? You? Yeah, just hit and you will get the log file on the right. So if we press here, we will get some information corresponding to the log file. Okay, we can do several times just for you to see. Okay, So this is the log file of running this model. Okay, the model is beyond the copyright and etc. or the license. Here is the model. Okay, so as soon as you get some information in the right side, you are running the model. That will work with Mac OS and Windows. The GAMS Studio opens the GAMS file, and just pressing that button, the green arrow, you will run the model. Okay. Then I'm going just to try to do with you 4 runs, okay? We will take 5 minutes, no more than that. So first, we will run for scenario 1, we will run for scenario 2, we will run for scenario 3, and we will run for the stochastic version of the problem, okay? And then we can write the objective function in a paper in order to save it, okay? So how we convert the stochastic model into a deterministic one? By opening the scenario tree. The scenario tree is called this tree. We can open also with this editor. So here you just drop the tmp tree.txt, okay, and you see the scenario tree. The scenario tree says that the first node corresponds to scenario 1. The scenario 2 opens from the second period, okay, and has a probability of 4.4. The scenario 3 opens in second period and also has a probability of 0.1, and the first scenario has a probability of 0.5. Okay, we have another scenario that is called mean, that is probability 0. Okay, so if we assign a probability of 1 to the first scenario, and then of course we delete the other probabilities, okay, and save it, Control S for saving it, okay, then we have converted our stochastic model into one deterministic, for just that we are assuming a perfect knowledge, perfect information regarding that the hydrogen flows we are going to receive in the next year will correspond to the ones of the scenario 1. Okay, just running again, we can see that the stochastic problem if we create a new file, okay, and we copy the value of the objective function for the stochastic problem, that was the first we ran. Then we have saved that information, so we are running just scenario 1. We can run it and copy the that information corresponding to the value of the objective function for scenario 1. Okay? Then we can modify and assign the full probability, the probability 1 to scenario 2, save the text file and run and do the second run, and copy the information regarding the objective function for scenario 2. Okay, and we can do the same for the third scenario and run it and copy the information regarding the third scenario. Okay, so if we assume perfect information, scenario 3 is, let's say, the wet scenario, therefore the objective function is smaller, okay? Scenario 1 is the average scenario, therefore the objective function is somewhere in the middle, and the scenario 2 is the driest scenario, therefore we have the highest value of the objective function, 1010, okay? And the stochastic solution provide us with something typically in the middle, 992 million euros, or $1 million, okay? So we have been able to run scenario 1, scenario 2, scenario 3, the stochastic problem with the 3 scenarios at the same time, and also, for example, we can run the mean scenario. The mean scenario will be the weighted mean, okay? So hydrogen flows from scenario 1 times its probability, that was 30%, times scenario 2, hydrogen flows of scenario 2 times the corresponding probability, and scenario 3, hydrogen flows times the corresponding probability. Weighted average, and therefore that is the mean scenario. If we want to run the mean scenario, just again change, okay, save, and then run it again, and we will get so that is again somewhere in the middle. So the deterministic problem either selects a priori the knowledge of the perfect information scenario, it's assuming that you know in advance which scenario corresponding to hydrogen flows is going to happen, or typically you select the weighted mean scenario, okay? By comparing the results, you know that in theory, the stochastic model, at the end, when repeating many times the same procedure, you will get better decisions. Why? Because you have included the information corresponding to the stochasticity by means of the scenario 3, that is the discrete time probability, and therefore you are protecting the operation of the system against the uncertainty in the different hydrogen flows. Okay, so that will allow you to run and to modify and to analyze the behavior of the system. You have the information you can export. Just if you open the GDX, anytime you have run the GDX is GAMS data exchange and corresponds to the numerical information corresponding to the decisions. So you can select any of these values, any of these parameters, and then export. And if you export, you can export to Excel and to JSON file, okay? And then you can, if you export, okay, this one symbol, okay. If you export it, you will have the numerical information in that location, and therefore you have all the details of how the generating units are being operated, which are the commitment decisions, which are the reservoir levels, which are the water value, okay? The water value more or less was defined by the first day by Javier. It corresponds to how much is the value of an additional unit volume, cubic meter, in your reservoir. So there is no cost associated to the water. However, if the value of that water will correspond to when is the best in the medium term operation of the system, where is the best usage of this water, when to keep that water for being used, and therefore which is the value of the technology you are substituting with this additional unit volume of water. Okay? Questions? Then I'm going to stop and pass the presentation to Javier that will continue with introducing you the network.